So is there anybody who hasn't covered kinetics
I
yet?
don't remember.
Where like you were looking at rate laws, changes,
Yeah. Okay. So first, let's talk about chemical kinetics. And what is the study of kinetics?
We're trying to find out how the rate of, how to say, the reactant disappearing and the product appearing or whatever.
So basically, you're looking at changes in concentration over time.
Yeah, that.
And why is that important? Well, let's think of it from an industry standpoint. Why is it important to know like how things are going to change with time? Well, what does time mean for a business?
Me.
Yeah, money, big money. So chemical kinetics is really important because in terms of the amount of time something takes, one, that's eating up valuable bits of your life that you probably don't want to spend like staring at some chemicals. And two, it's going to cost the business some cash. So these are really important things. All right, so what was the goal of today's experiment?
To determine the rate law.
Yep, determine the rate law of the reaction of what? What are the two species that were reacting together or would be reacting together?
Blue dye.
Yep, the
And
blue dye.
sodium hypochlorite.
Yep. Okay. So basically, what's happening is we have our blue dye, number one, or brilliant blue. It's reacting with the hypochlorite anion. And we get some products. Okay. How are we going to keep track of this? Or how would we keep track of this? So in the pre-lab we talked about how are we going to monitor this reaction? How do we know it's going to completion?
Changes in absorbance.
Yeah, changes in absorbance. So what color do you think this blue dye is?
Blue.
Yeah, it's blue. Okay. This hypochlorite, has anyone ever seen bleach? This is the active ingredient in bleach.
Oh.
So if you pour it out, what's it look like?
Clear.
Yeah, it's clear, it's colorless.
Yeah.
And then our products, if you let this whole bleaching process happen, have you ever taken something that has like a stain in it and you hit it with bleach? What happens to it?
Takes all the color out.
Yeah, so this is also colorless. So if we keep track of how much blue light this sample, or how much light is being absorbed by these systems, what's the only thing that's absorbing light out of these? Visible light.
The blue dye.
Yep, the blue dye. So if we look at how much that absorbs over time, we're actually keeping track of its concentration. And we'll come back to that in a minute. Okay, but now what about the rate law looking at this? Let's say we were coming up with a generic rate law. We have rate is equal to something. What else do we need here?
K.
Yep, we need a K, so a rate constant. And we only care about the concentration of our products, or excuse me, the concentration of our reactants. That's what determines the speed of a reaction. We're going to have dye, and we're going to have OCl minus. We're also forgetting one thing here. What do we need up here and up here?
Coefficients.
Yep, coefficients. We're going to have X and we're going to have Y. Okay. Can we tell what X and Y are right off the bat?
No.
No. So how do we figure out X and Y? And what are these things called? What are these coefficients called?
Order.
Yeah.
Yeah, that thing.
Orders are determined. So how do we figure out orders?
Yeah,
I
like-
like
Graphing out the value.
reactants and products.
Yeah. So where are we getting that stuff from?
data.
Yeah, data. You actually have to do an experiment to figure out these orders. So they're determined via experiment. And that's truly the only way you can find this rate law. The other times you can do this is, did you guys talk about elementary reactions at all?
One-step reactions.
Yep, like one-step reactions, and they're called elementary reactions. So if you break down the mechanism at which this is happening, these are the simplest steps. So you can also look at the stoichiometry. If, and if is a big deal, and only if it is an elementary. So most problems will tell you if it's an elementary reaction or not. If it doesn't say it, you have to go with experiment. Okay? Everyone feel comfortable with that? All right, cool. All right, so let's talk about the isolation method. So we're using a method today called the isolation method. And in this method, what we do is we have all reactants present, but one is present in a large concentration. So what reactant is going to be in a large concentration for us?
The dye.
Nope, not the dye.
The other one.
Yeah, the other one. Yep, the hypochlorite. So in our case, the concentration of the dye is much less than the concentration of the hypochlorite. How does that benefit us? Well, how much, so we can have a relationship between the hypochlorite initial, so the initial amount that we put into our system, and then we have, after the reaction is done, we have hypochlorite final. If there's so much more of this, what can we say about the relationship between these two?
It's
Well,
a positive difference.
It's definitely going to be a positive number, yep. What else can we say? Are these going to change very much? So I'm sorry, what was that, Arden?
I said the change would probably be negligible if it's
Yeah,
so
it'll be,
much.
It'll be really small. So what we could say is we can approximate these two things to be equivalent to one another, because the concentration of the dye is so small, it's not reacting much with this hypochlorite. So not much hypochlorite is going to be gobbled up. Okay, so let's see how that impacts our rate. Let's jump back to our rate law. We said rate is equal to our equilibrium constant. We had our dye raised to the power of x, and we had our hypochlorite raised to the power of y. So can we simplify this in any way? Or does anybody have any ideas of what we could do? Well, let's look through, let's determine what's going to be a constant. The rate's going to change as we move along. This K is going to be a constant, right? The concentration of the dye, is that going to change throughout the course of the experiment?
So it's like 0th order or first? That's 0, right?
Well, we'll talk about what that order is in a minute. But the question I have is the concentration of the dye going to change through the experiment?
No.
Well, we said that when we were keeping track of stuff, the dye is blue and the products are going to colorless, right? So how do we know the reaction is done or is complete?
Oh, if it's colorless.
Yep, and it's colorless. So is this concentration of the dye, is that going to remain constant?
No.
No, right. So not constant. What about this guy?
Yeah.
Yeah, we can approximate it to be constant. That leads us to a new rate law that we could write. We could do rate is equal to K prime dye raised to the power of X. Why can we just get rid of this term here? What have we done to it?
Since it remains constant, would it be like what her job was saying earlier, 0 order? So we get rid of it.
Yep. What we're doing is we're just taking this and flinging it into a constant. So notice how K prime and K are actually different. This value right here will be a constant, and this is known as a way to approximate this system. So therefore, that's what our rate law is going to be. So question, we're going to ask a couple of questions. What we're trying to do in this lab is figure out what is the value of that X. And we're going to talk about ways we can do this. Since we don't have the experimental setup in front of us, we're going to have to do a couple of questions, kind of give an idea of why we're doing what we're doing and the data that you have available. So the question is how do we do this experimentally? So how are we going to do this experimentally? Anybody have any ideas?
We like measure the absorbance versus time first.
Mm-hmm. So we measure the absorbance of dye over time. And how do we measure that absorbance? What instrument do we use?
Spectrophotometer.
Yep. Okay. So how we have a relationship where we have absorbance and we say it's proportional to concentration. There's a law that actually lets us go from this proportionality to an equal sign. Do you remember what that law is? So this little Jesus fish, this means proportional. But we want to change that from a proportionality to an equal sign. Anybody know how we do that? Or anybody have an idea of a law that can be used that relates absorbance and concentration to one another? Give you a hint, starts with a B. And ends with an ear, Beer's law. Yeah, there we go. Does anybody remember what Beer's law stated? Absorbance is equal to what? Or have you guys ever, I think we've talked about Beer's law once or twice, haven't we? Or no, have we not?
Think so. I don't know.
Okay. We have epsilon BC.
Yeah, no, we haven't.
Okay, you had seen that one? Oops, moving the camera. Ah! Having some issues. Okay. There we go. Okay, let's talk about these things. Absolutely. Let's define what these terms are. What's A?
Absorbance.
Yep, this guy's absorbance. What's C?
Concentration.
Yep. Anybody know what B or E are?
Is B Beer's law constant?
That's actually this guy. It's called the molar absorptivity. And what B is actually the path length. Okay. So let's draw a schematic of a spectrophotometer. Have we ever done that before? Okay. So let's think about, we want an instrument that measures the absorbance or how much light passes through a sample. So I'm gonna sneeze. There we go, manager.
Bless you.
Thank you. So let's say we want to build a device. We want to build something to measure the absorbance over time. We have to think of what we need to build this instrument. So can anyone tell me what we're going to need to shoot light through something and measure it? Any ideas?
Light. Like
Yeah,
a
we need light. So we need a
Yeah.
source. Light bulb, woo! Okay, we have a source, which is not in focus. There we go, now it's better. Oh, it's passing on us. Okay, we have a source of light. What else do we need? Well, we probably need the thing we're going to measure, right? Let's put our sample in there. And the sample's held in a cuvette. Actually, we have blue, so I'll use blue for our dye. So there's our sample. Now, have you guys ever seen a cuvette before or no? Yeah, it's a little plastic thing. Some of them are made out of quartz. The quartz ones are extremely expensive. How big is this thing? Anybody have an idea?
Oh.
Let's say we wanted to make the math easy. Remember, this is B along here. If you wanted to make that easy, what value would you give that?
1.
1.
1, yep. This is 1 centimeter. You can find other cell sizes, but generally they're 1 centimeter to make your life way easier. Okay, so now we have a source, we have our sample. What else do we need? Are we collecting any light right now? Or are we measuring anything?
Like a sensor, I guess.
Yeah, we need a sensor, we need a detector. Most of these detectors are photodiode arrays. They look at how much light of certain wavelengths is hitting the detector. We're going to draw it as an eye. You don't want to stare directly into a light, but we're going to draw it as an eye. So I don't know, we'll make the person have red eyes. They're a demon or something. There we go. Here, we'll make it my eyes. There we go. We have a detector. Okay, so tell me what happens then. We have these devices. What are we going to do? So tell me how this thing operates.
Gotta direct the light to the sample.
Yep. So we got to direct the light to the sample. Okay, we have a mechanical slit that lets the light go through. It hits the sample. It goes through the sample and goes to the detector, right? But there's a problem here. All the wavelengths of light are coming in at once, so they're all hitting at the same time. What would you do to make sure only one wavelength or a given wavelength made it through the sample or made it to the sample? What would you do?
Filter it.
Yeah, you'd filter it. Now, can you think of any simple ways you could use to filter light, making like splitting light into its components?
Magnifier? I don't know.
Like a
Not a
crystal.
mag-
The crystal, yeah.
Yeah, a crystal, a prism. And what happens is the light of different wavelengths gets separated out, and you get the one that you want. Let's call that H nu prime. We see how much enters and how much leaves the system, and we measure that. So that's how a spectrophotometer works. Everybody feel comfortable with that? How many people used one? Is there anybody who used one in like bio? I think you guys did that before you left.
We did a lot last semester.
Yeah, did you? Was it fun or not really?
No.
Chemistry is way more fun.
Yeah.
I don't know about virtual chemistry though. We'll see how fun that is. Okay, so that's what we're measuring, and that's what these things mean. That path length again is just how much of the sample we have. How far is the light traveling? Okay, so next question I have is we run our experiment, we collect this data, but how do we know the order? So once we have our data, how do we determine the order? So luckily you guys don't have to go through and collect the data. The data is all online for you. But let's say you collect your data. How would you analyze it? What are you going to do next?
You compare experiments.
I'm sorry, Carrie, what did you say?
Don't you compare the experiments?
We could compare experiments where we look at different concentrations, right? Like you've done in class. However, this time we only have one concentration.
Plot it.
So, plot it, did you say?
Yeah, so you can find the slope of the.
Yeah, so we're going to plot it. There are a couple different ways. So we plot it using integrated rate laws. So does everybody have their manual with them? If you look on the second page of the experiment, you should see something that looks like this. Did you guys talk about those integrated rate laws at all in class?
Yeah.
Okay, so you guys know that if you want a straight line, you've got to plot these guys. The way we're going to know the order is we're going to determine which one gives us the best linearity or which one is the most straight, right? Okay, so now let's say we take our data and we want to know if it's second order. The question, how would we determine if the order of the reaction was second order? Sorry, that's a was. What is the integrated rate law for a second order reaction? So what's it say in the manual for a second order?
Over concentration of A
Mm-hmm.
equals KT plus 1 over the concentration at 0.
Yep. Let's talk about what these things are. What is T? That's a bigger one.
Time. No?
Yep, time. Okay, this A naught. What's A naught?
Initial concentration.
What's A sub T?
Concentration after like certain amount of time passed.
Yep, concentration at time T. What's K?
Rate constant.
Yep. Okay, this is actually a linear plot. What's my Y in this case? Or what's my X?
T. T?
M.
I'm sorry, what'd you say, Phil?
M.
You're breaking out again, I'm sorry.
Is it just time?
Time is which one, X or Y?
X.
Yeah, this is X. What's K then?
Oh.
M.
Yep,
Or
slope. M. What's my Y then?
1 over A to
Yep.
the T.
And then what's this guy here?
B.
Yep, B, that's your intercept. So the reason these guys have these crazy looks to them is because they're actually a linear, they're trying to make this so it's a linear line. Which sounds like an oxymoron, well, sounds super redundant. To make this into a linear equation, excuse me. Okay. So now, so what we would do is what would you plot? What's
Linear
gonna be-
line.
Yep, you're going to plot 1 over adsorbance versus what? That's your, yep, time. And you see if the regression is linear. So if you notice in our integrated rate law, we had concentration, but I said plot 1 over adsorbance. So the next question we have, am I okay to move this or do you need me to go back? We're good? Okay, next question is why 1 over adsorbance rather than 1 over the concentration of A? What allows us to do that? Or why would we want to do that?
Beer's law because they're proportional.
Yep. Absorbance is proportional to concentration. And why is it beneficial to use absorbance rather than that concentration?
We don't know the concentration.
Yeah, we would have to know the molar extinction coefficient. It means more manipulation, more data that we have to deal with. So just working with absorbance makes our life a ton easier. And that's what we're going to go with. Okay, next question. How do you know if your data has a linear relationship? So what do you look at to quantify how linear a relationship is? Does anybody know? Like if you're doing some statistics.
Like the slope, if it stays constant.
You can look at that, yep. There's also another real easy measure that a lot of people use in statistics. Anybody know what that is? Have you heard of R squared before?
Mm.
Yeah. If something is linear, what is the value of R squared? Like if it's perfectly linear. Anybody know? Yep, 1. So if the R squared value is close to 1, you have a model that fits pretty well. This is keeping track of the least squares fit model that allows you to see how linear something. All right. Cool. I think with that, we've covered pretty much everything that you need to conduct the lab. Everybody is going to produce their own worksheet today, and you're going to send that, but you can work in groups. We're going to break people into, I don't know, groups of 3 to 4. Are we okay with going with our same lab benches that we had?
Mhm.
Okay. Are there any questions we have before we break off into that group?
Also for the Excel, is that like we'll send that separately to you with like
Yes.
our PDF? Okay.
Yep.
So
Yep. You
just
can
share that the same way.
Yep. You can share it, or you can just email it to me, whatever way you want to do it. Okay. I'm going to break people into groups. We're going to have 3 groups. Well, how many groups? We have 4 groups traditionally, right? We'll break people into groups so they can interact with one another. I will try to float between those so everyone can see what's going on. Any other questions? No? Okay. I'm going to quit recording.